In this episode, we're going to talk about generative adversarial networks, or in particular, generative models that in this episode, we're going to talk about different kind of neural networks that allow to generate objects of certain kind. It could be images, it could be sound, it could be some tabular data set. And really, we'll take a look at different examples in a couple of slides. And generative adversarial networks are just one of the approaches that can solve such a problem. So let's consider a more generic problem settings. So we have a training data, photos of something or text or speech, and we want to build a model that would allow to sample objects that are similar to our given data. So we assume that there is a population distribution, and we want to replicate this distribution by our neural network. And if we build such a network, we will be able to sample more objects from this network. And it might be helpful, for example, for data augmentation, or for various reasons, like producing deepfake videos or something like this. Variety of creative professions. You can generate textures for three-dimensional modeling. For data privacy, you can publish samples without disclosing private information from the original data. Or you can apply it to physics or engineering sciences to build a model that will produce some kind of stochastic output of an accurate but slow simulation algorithm. And to learn more about current state of the art of generative models, I would encourage you to visit site ThisX Does Not Exist. You will find a lot of cats, a lot of people, a lot of rooms that has been generated purely by neural networks. So, and here is the style transfer example that starts with a general picture, photo, and during a network that has been trained on the paintings of certain artist that is known to work according to certain style rules, and it transforms the original paintings into, for example, Van Gogh style. And I would encourage you to look for more details at this website. And this field has been growing quite rapidly, so since 2014, when pixels or images was quite basic and low dimensional. Now you can generate quite high accurate images, high dimensional, and even plug those images into movie scenes that allow you to generate these deepfake movies that you probably have seen before. So one of the basic approaches that helps to deal with such a problem is called generative adversarial networks. So we start with a basic architecture, and input for such an architecture would be a random noise, and it usually multidimensional noise, and output of such a network we expect to be a generated image. Since this network is a differentiable function, we can optimize those weights in such a way that it would gradually converge to the more and more accurate production of the images that we want. The only thing is how do we compute the error to estimate the gradient. And first of all, we have to rely on differentiable measure of similarity between sets of generated and real images. So one of the ideas that underlies generative adversarial network approach is that we can introduce another neural network that is only useful for discriminating between generated and real data. And we just rely on the characteristic like entropy, cross entropy of the discriminator network to understand how good our generator network is. So if we add some math here, our noise would be represented by ZI letter, and PZ is some kind of PDF that we can sample from. So it's multivariate normal distribution, for example, and we want to generate samples in the form of this generator network that depends on parameters theta and takes ZI as an argument. And then we have a discriminator network that is parameterized by different set of parameters phi, and it takes an X like image and returns the probability of X being a real sample. So the measure similarity between the generated and real samples that we want to minimize is first we want to make it as high as possible. It's basically a cross entropy of the discriminator. So we sample from real images, and we want to be predictions of those images as high as possible, and then we sample from the noise and pass the noise through the generator, and we want to be discriminator as small as possible, and in total it is essentially a cross entropy function that we want to minimize with respect to weights theta. So in this total loss function is adversarial loss in which two different networks, d phi and g theta, are competing against each other. So the discriminator wants to be able to find all the details of generated samples, and generator want to mimic the reality as much as possible, as accurately as possible. And here is the algorithm that follows the procedure, and it's just a quote from the paper, original paper in 2014. So, in interesting example of this adversarial loss with respect to original loss cross entropy that we usually use for regular convolutional neural networks or fully connected, is that in this example we build a model that learns the loss function for us. So it depends on parameters of discriminator that are optimized implicitly during the training. So possible problems that we may encounter with GANs. If we just rewrite a little bit loss function and expand the expectations as integrals through the distribution, for example, P generated by our generative network. So it's relatively easy to show that the maximum of with respect to phi is obtained at such phi star that depends on theta with the formula depicted here. So if we have such discriminator that has follows the optimal ratio of likelihoods, like likelihood ratio. And in that case, the objective becomes the following. So we just substitute this thing into here. And it can be rewritten as logarithm 4 and Jensen-Shannon divergence between distribution P and distribution P generated that depends on theta. And in case P and P generated have no overlapping support, it could be that a loss function would equal to 0, effectively to 0. And it means that there will be no gradient that would guide us to the correct direction. So the network will not be able to learn. So it is essential for P and P gen to have the same overlapping support. Another problem is called mode collapse. So let's assume that at some point the generator has learned one of the models. And we can depict the data, that original data has two modes that you have here and we have here. And assume that the generator has learned the second mode. And it's easy to show that there is no gradient that would ever move our generator out of the first mode to the second one. So gradient is not very helpful at shifting our learned distribution to match the second one. And to address this problem of mode collapse, we can use a little bit different architecture that is called Wasserstein GAN. This main difference lies in the way how to measure similarity between real and generated samples. So there is so-called Wasserstein distance, or it has a separate, different name, that is Earth movers distance. So in case we have two distribution P and Q, in case we have two distribution P and Q, and we can consider those as two dirt piles, and we want to see how different those distributions are, and we do this by estimating amount of work we need to move dirt from one distribution to another. And we can split into slices and just illustrate that the work that is needed can be depicted as moving those pieces around from one distribution to another. And the cost of moving a certain amount of m from one position to another is proportional to this amount and distance between those positions. And earth moving distance between two distributions is the minimum total cost of converting P into Q. So why this distribution is, why this measure works better than GAN we shown before. So if we have two densities of a real and fake images, like blue and green ones, the GAN discriminator gradient is depicted by red, and you see it has a very steep curve and doesn't allow to move from one place to another, while the gradients in W in Wasserstein GANs have like a regular curve, following which we eventually move to the real data sample distribution. So here is the formal definition of the Wasserstein GAN. So if we have a moving plan gamma that is correspond to the difference between two distributions, or how much dirt we want to move from one place to another, then cost of moving would be proportional to the distance and to the plan integrated by all the intermediate steps, and the total cost would be the following integral, and we can rewrite it as the expectation of x1, x2 sampled from this moving plan distribution and the modules between x2 and x1. And if we want to convert the whole distribution, our plan has to satisfy those two constraints. So in original, it has to be equal to, in original x1, it has to be equal to q, and at x2, it has to be equal to p. The integral has to be equal to p. So coming back to Earth mover distance with respect to Wasserstein GAN, we can rewrite this distance as an infimum across all possible plans, such that transform one distribution to another. And since optimization across all possible plans is not too easy to compute, we can imply a little bit of dark magic here. So if you're interested, I would really encourage you to have a look at this link that describes all this magic in a little more details. But in principle, we change the infimum to supremum over all possible functions, such that give different answers for samples from real distribution and from simulated distributions. And such functions should comply with Lipschitz one continuity constraint, which is the following thing. The difference between function values in two different points is less than distance between 2 points multiplied by a certain constant. And this constant is essentially the same thing as in the name. So if it's Lipschitz 1, it means that the difference between the values of functions is less than the distance between two points between which we compute this difference. It means basically that the gradient in every point is restricted by this number k. And then we can substitute the discriminator from the GAN function, from the GAN model that we described previously, with this function f, or critic, across which we want to find the supremum of this expression. And this would be the Earth-Mother distance between two distributions that we want to minimize by training the generator to replicate our real distribution as close as possible. And the expectations can be estimated as a sample mean over the patch, and Lipschitz 1 continuity can of course be replaced with Lipschitz K continuity, but in this case we would estimate K times Earth-Mother distance, but it doesn't matter much because we want to minimize this Earth-Mother distance thing. And as a rather rough estimation of this property Lipschitz 1 continuity, it is possible to clip the parameters of this function f. So suppose we have this f defined by set of weights, and we just restrict that those weights do not get outside of some range minus c. We'll see how the training of this algorithm works. The only thing I would add here is this fw, of course, is a neural network, and w is set of weights that we want to optimize during the training of this critic. And here is the algorithm that goes from the initial parameters of critic, initial parameters of generator, and the external cycle is iteration of generator weights update, and this internal cycle is training of the weights of the critic. So we sample data from the real sample, from the prior samples, and then we compute the gradient of this Wasserstein distance. So it's basically the same expression that we saw here of Earth-Mother moving distance. We compute the gradient, and since we want to maximize it, during the gradient step, we add it to the weight of the previous iteration. And to avoid too large values, we clip weights by certain parameter c. And after n critic iterations of this internal cycle, we proceed to the training of the generator, and that basically follows the gradient descent here. So it's a workable approach. However, the dirty trick here is clipping the weights. So it's not very meaningful, because at certain point it can result in really flat values that doesn't allow the gradient to pass through these iterations, and it will vanish and stop all the training procedure. So on this plateau we will not be able to go neither left nor right, and this is something to be avoided in the neural network training. And thus 3 or 4 months later, an addition to the original paper has been issued that is called Wasserstein-GAN with gradient penalty, that addresses exactly this issue of the weights clipping and the gradient vanishing. So, and the observation was that for function Lipschitz 1 continuous function f, this function should be restricted by the gradient of this function, and thus we can replace weight clipping with a gradient penalty. This gradient penalty term is written here, or alternatively it could be a one-sided penalty like here. And for more details, you can refer to this paper. And here are examples of the distributions that this approach has been able to generate, and actually there are many more examples that you can generate with this approach. And thanks to this gradient penalty trick, it was possible to train very deep neural network for generating realistic images. So in this picture you can see how different GAN approaches deal with images, and you can see that the rightmost column of this table looks like the most realistic one. And also it allows to like dealing with 101 ResNet layers that produces quite sharp images. Okay. Next few slides, I'd like to mention some notable architectures that are used for generative networks. So first and probably most useful is using conditional GANs, or conditional distributions. So instead of learning probability distribution of X, we want to learn condition distribution depending on some parameter A. So for example, if we want to generate a face of a person given hair color, skin color, a facial expression, etc. And we can do this by changing the distribution of our, or changing neural networks, generator and discriminator, into parameterized form. So we supply those A parameters to the generator and discriminator during the training. Here is the illustration. So we have these conditions, and for the generator we send those conditions to the input layer along with latent random noise. So we get this X prime simulated, and we also give those conditional values to the discriminator. And this is it. Next approach is called pix-to-pix, which essentially maps one kind of pictures to another kind of pictures from one domain to another. And here are some illustrations. So from satellite images to maps or from some labels to architectural facades, from black and white to color images, and for edges written by hand to the photorealistic display of the images of the same kind, etc. You can play such generators at the website of the author of this paper. Next illustration how you can train a really fine detailed gun is so-called progressive growing guns, which start with lower resolution images like 4x4 and tries to replicate, discriminate such low-res pictures from the real one, and as it achieves a significant quality, it adds one more layer of twice larger along each axis, so 8x8, and then iteratively it goes 124 times 124, and you can see that it allows to generate rather highly realistic facial images. So how do you compare two different models for your practical needs? First of all, there is no single guide to follow, and usually approaches are very problem specific. So perceived visual quality for facial images can be very different from the quality of generated dental crown model. And most solutions are adapted or invented for a given particular task. So anyway, but there are some general approaches that people follow. If you have a small data set, you can afford by eye comparison. So it's a little bit unpractical, but if you have some specific needs, maybe it is way to go. Otherwise, we can compare some physical characteristic. In case of physics, we can afford this, like means, medians, or standard deviations, or correlation between generated features. Or we can do some statistical tests like chi-squared or Kolmogorov-Smirnov between either individual dimensions or projections of the objects produced by our generator. Or we can plug in additional classifier that can be trained on independently to distinguish real and fake samples, and then we evaluate our gun by checking the classifier score, like area under ROC curve. So it is like objective quality measure, although it can be resource consuming and requires some hyperparameter tuning. And also it may get picky to things that might be not important for the downstream task that we plug our generative model into. Let's consider another extension of this idea of training an external classifier. In this case, we take an let's consider further the idea of adding another classifier on top of trained GAN model for evaluation of the quality. In this case, we rely on an inception model that is pre-trained image classifier on ImageNet, and we can use it to obtain conditional label distribution for each image X that was generated by our model. or real one, but in this case we compute this score only using generated images. So there are two considerations that since images produced by a generative model can be sometimes rather vague, you don't know if it is an image of a cat or image of a dog or whatever, and a good, nicely trained generative model should generate low entropy images of a specific class. So Inception should be very confident with respect to what is generated there. So if we have, say, 10 classes, then we should be able to see a narrow peak along the number of the class that we have generated. And on the contrary, if we take a whole sample of generated images and we can compute a marginal distribution across all possible generated samples, and this distribution should be rather wide. So it should be something like these. And it means that those distributions should be rather different. And one of the way how to compare the distance between those distributions is called Kullback-Leibler. And we can just average this distance across all samples that was generated maybe within a batch, and then we take exponent to compare those numbers with simpler. And this gives us a so-called inception score, which is the higher for more realistic generator. And the next approach that is somehow improved version of this inception score is called Fréchet inception distance, and it deals with the drawback of the inception score that doesn't rely on real data distribution. So instead of comparison the distribution of the conditional outputs of the model, we can compare some activations at some layer, like last pooling layer, for example. And authors propose to compute Fréchet or Wasserstein-2 distance between multivariate Gaussian approximation of real and generated samples that was estimated at this last pooling layer. So in this case, the smaller this number is, the better generated distribution is to the distribution of real samples. So it was just a scratch of a surface, and there is a variety of different measures that you can plug in to compare generative models. And this actually brings us to conclusion of this talk, and I would like to outline that generative models and GANs in particular is a rather broad field of machine learning. And there are lots of different architectures, and this lecture is just a scratch of a surface. And GANs is like a special kind of machine learning algorithm, because it doesn't only learns the weights to approximate something, but it also learns the loss function for this generator. We considered an alternative to vanilla GAN that's called Wasserstein GAN that enables really deep networks to be used for data generation. And we considered the quality estimation method that still continues to be an active topic for research. So thank you very much for your attention.